Howdy gang, welcome back. I apologize if you hear some fan noise in the background, the meeting from my previous class, that video recording is converting. I also want to apologize for the delay in getting the recordings up from the September 1st and September 3rd classes. I had some issues with my computer. I think I shared that with you. Hard drive space and the cloud keeps fighting me. But I did finally get those moving. They are uploading as we speak. So you should be able to watch all those old class videos anytime later today. Today, we are going to begin the hard part. So sorry, we pick out those notes. So 5.5 use substitution, 6.1 areas, all the other chapter 6 stuff like volumes, work, and average value. All applications of the definite integral or applications of integration in general. But we had to keep those problems very tame. There are not a lot of functions for which you could find the average value because there are not a lot of functions you are able to integrate at this point. But starting today, we're going to fix that. Starting today, we are going to learn how to integrate more shit. And this is really the bulk of the material on exam 1. So thus far, things have been fairly gentle. Don't misunderstand me. The stuff that we've done so far is important, but it's not as important as what we're about to do. So just to remind you, right, we've been looking at some nice applications of the integral. But starting today, we are moving into chapter 7, which is all about different integration techniques. And we'll be doing this for the next 3 weeks. Next 3 weeks is going to be all how to integrate more and more and more and more functions. Because, you can differentiate a lot of stuff. I write down some random combination of exponential sines, cosines, polynomials, square roots. I expect that you guys can calculate those derivatives, no problem. If I write down any one of those random combinations of exponential sines, cosines, polynomials, and roots, integrating is not so likely to work out. And in general, you'll see that integrals, and you start writing down random shit, even after I've taught you every method there is, odds are you're not going to be able to find an integral of it by hand nicely. However, that's not to say we can't broaden the world of things we know how to integrate. So today we're going to begin our journey, which is, most people think of Calc 2 as having like 3 parts. The first part is integration techniques. The second part is like sequences in series, power series, and the third part is applications. We've done some of the application stuff, but today we're going to dig into the first real meat here. This, of course, is MAC2312, which is a Calc 2 class. The section number is 004, and the date is the 8th of September, 2021. Today, begin integration techniques. Specifically, we're going to look at integration by parts. I'm going to put the dog outside. I will abbreviate integration by parts as IBP. This is section 7.1. So I'll tell you first, integration by parts is a backwards product rule. Right? You have a product rule for derivatives, like how do you differentiate x squared times sine of x? You use the product rule. How would you integrate that? Integration by parts. All right, let me put the puppy outside. We'll get into it. Miss Wallace. Okay. Let's do it. So this is integration by parts, which is a backwards product rule. Right now, we know how to integrate obviously, I'm not going to list everything, but we know how to integrate stuff like, I'll just use the example I gave you, stuff like x squared and sine of x. But how would you evaluate the integral of x squared times the sine of x dx? The first thought you may have, which is the same thing as the first thought many people have when they are asked how to differentiate that, is not correct. So the integral of x squared times the sine of x dx is not what you get by integrating each piece on its own and then multiplying them. In other words, this is not equal to x cubed over 3 times negative cos of x plus c. Right? You cannot just integrate the x squared and integrate the sine x and call it a day. Unfortunately, that's not how it plays out. But you should be able to kind of smell that coming because you know the derivative of x squared times sine of x is not 2x times cos x. Or similarly, you could say, you know, if you differentiate this thing, it's a product, you would have to use the product rule. You're not going to get this thing. What does work, and I'll prove it to you, is the following. There's two versions of this. And I'm going to write it. Write it like this. Now here, u and v are both functions. So dv is a differential. It's going to involve some function stuff. And du is a differential. It's going to involve some function stuff. And there's a version of this for definite integrals. It says that the integral from a to b of a product of the form u times dv is equal to u times v evaluated from a to b minus the definite integral from a to b of v times du. So for the definite integral version, you just put the evaluation brackets in there. And this is where u equals u of x and v equals v of x are functions. Now this might look weird. It doesn't immediately look like a product rule thing, right? This looks quite different from the product rule. But let me rearrange some stuff for you. Do a quick proof. So if the integral of u dv is equal to uv minus the integral of v du, I can add that integral from the right-hand side over here. And we see that this is equivalent to saying that the integral of u dv plus the integral of v du is equal to u times v. I'm not assuming that this is true. I'm just saying this is equivalent to this. I'm just adding this integral to both sides. Now differentiate. Remember, u and v are both functions of x. So if you apply d dx to both sides, on the left, you have d dx of the integral u dv plus the integral v du equals d dx of u times v. And then by the fundamental theorem of calculus, the derivative and the integral cancel each other out. And you just get u times, this would be v prime plus v times u prime is equal to the derivative d dx of u times v. And this is the product rule. For derivatives, which we know is true. So that's it, that's the proof. The big step here where you go from here to here, this is the fundamental theorem of calculus. So this statement right here is a true statement because it's logically equivalent to, by the fundamental theorem of calculus, the regular product rule for derivatives. The trick to using integration by parts is identifying your integral as u times dv, or your integrand, I should say, the thing inside the integral. You take your integrand, the thing you're trying to integrate, and you call part of it u, and you call everything else dv. Within dv, you always place the differential, the dx or dt or d theta. But you need to do what's called partitioning. You need to partition your integrand into two pieces, one of which you call u, the other which you call dv. Then you go off to the side and you calculate all the pieces here that are not u and dv. So we know we're going to need a v. The way you go from dv to v is by integrating. And we know we're going to need du. The way you go from u to du is by differentiating. All right. So, got to remember this. Believe it or not, this is the whole thing for section 7.1. Let's see how to use it. Let's evaluate the integral of, let's just do x times sine x. X. Rather than x squared. Let's keep things simple. The way I'm going to do this is by splitting this integral up into pieces. This first piece here I will call u, and the second piece here I will call dv. We're not making a substitution. I want to be clear about that. This is not u sub. For that reason, in the future, when I make little u subs, I might use a different letter. I might call them z or something. If you're going to do integration by parts and a u sub on the same problem, then you really need to be careful about how you label your variables. Because the normal way of writing integration by parts is with the u's and dv's. I'm going to use that notation. So you take your original integral, one piece you'll call u, everything else you'll call dv. And I'll give you some guidelines for how to split this up, but not right now. Then you fill out, I call it the little IBP table. So we chose u and dv. I chose to make u the x part and everything else, sine x dx, to be dv. From these, we need to calculate two things. I need to calculate du, and I need to calculate v. To go from u to du, you take a differential, right? You differentiate. So the derivative of x is 1, so the differential is 1 dx, or just dx. To go from dv to v, you need to take an antiderivative. You need to integrate, right? I integrate on both sides. So the integral of sine x dx is negative cos x. And we don't write the plus c, right? When you're filling out your little IBP table, you don't write the plus c. Then you apply the formula. The formula says the integral of u times dv is equal to u times v minus the integral of v times du. So from my table, u times v, that's x times negative cos x. I may have to let that puppy back there just a second. Minus the integral of v times du. So that's negative cos x. And then du is just dx. So take a second here, make sure you're comfy with where everything in this table comes from, given this choice of u and dv, and then verify for yourself that this is correct. I'm gonna let the dog know. Stop doing it. All right. Any questions about where anything on this last line has come from? Okay. So you start with an integral, you cook up your IVP table, and you get some shit minus a new integral. And the hope is that this new integral is easier than the original integral. If the new integral is harder than the original integral, you've done something wrong. You've chosen u and dv poorly, or maybe integration by parts just isn't the method for that problem. But if you've chosen u and dv wisely, and the integral is amenable to integration by parts, then this integral will be nicer than the one you started with. In this case here, we get negative x cos x. And then the minus minus here makes plus, right? You can pop that negative one out, plus the integral of cos x dx. And the integral of cos x dx is one I know how to do. All right, what is the integral of cos x?
Sin x.
Sin x. So this is negative x cos x plus sin x, plus a constant. Maxwell, get down. So I claim that the most general antiderivative of x sin x is negative x cos x plus sin x plus c. And we can check your work. If you want to verify that you've done an integral correctly, you take the derivative of this and see that you get that. So just real quick, let's calculate d dx of negative x cos x plus sin x plus c. You know that the c is a constant. He's going to differentiate to 0, so I'm not going to worry about him. God, sorry. Maxwell. No. Stop harassing these damn cats. Sorry. So this goes to 0. This, we know how to take the derivative of sine, it's cosine. This requires a product rule. So this is going to be, I'll pop the negative out of the first piece, negative d dx of x cos x plus, I'll write it here, why not, d dx of sine x. And the plus c differentiates to 0. I'm not worried about him. This negative is this negative. The derivative of x cos x, that's a product rule thing. You differentiate the x, leave the cosine alone. That's 1 times cos x. Plus, now you leave the x alone, differentiate the cosine. That's x times, well, what's the derivative of cosine? It's negative sine, right? Negative sine x. That's that first piece. Then the derivative of sine x is cos x. So what do we have all together here? Distributing this negative, I have negative cos x, and then negative times this piece, which is negative x sine x, is positive x sine x. And then plus cos x, chilling at the end. And negative cos x plus positive cos x is indeed x sine of x. So were we correct? Yes, we were, right? The thing we thought was the antiderivative for x sine x is indeed the antiderivative for x sine x. Choose. Right, that's the only time I'm going to do that. But if you want to check your integration, differentiate, right? That's what the fundamental theorem of calculus says. Let's go back up to the problem itself and see where the challenging steps are. So for this one, there's really only one. Where did we need to be creative? Where did we need to use our brain? Well, calculating du here wasn't hard, just taking a derivative. Calculating v here, that wasn't hard. That was just a really basic antiderivative. And everything that followed was just, a little bit of algebra and then another basic antiderivative. The only hard part was this, choosing u and dv. If I had swapped those around, if I made this u and this dv, the table would look very different. And the resulting integral would be much harder. So the creative step here, the step that requires some thinking, assuming you remember your Calc 1, right, where you find these basic derivatives and antiderivatives, then the hard step, the only hard step, is choosing u and dv. I'll give you a rule for this. There is a mnemonic. I don't know how to spell it. There's a rule for this. There's actually multiple rules for this, but the version of this that I find the easiest to remember and works the most is LIPET, which stands for log inverse polynomial exponential and trig. So LIPET, L-I-P-E-T. What does this rule do? Well, think of this as a hierarchy, and it's a hierarchy of things you should choose for u. So the way we do this is we pick the u, and then everything else is dv. Use LIPET to pick the u, and then everything else is dv. So what do I mean? How do I use LIPET to pick the u? Well, I look at my integrand, I look at the stuff inside, and I ask, are there any logarithms? If there are any logarithms, I should pick that piece to be u and everything else to be dv. Okay, no logarithms. Are there any inverse functions? Those are like arcsine, arctangent, functions defined to be the inverse of another function. Technically, a logarithm would be an inverse, but for these purposes, we think of logs as being before them. So is there an arcsine, an arctangent, arcsecant, any function defined as the inverse of another function here? No, no, there's not. Are there any polynomials here? Fuck yes, there are. X is a polynomial, all right? This is a polynomial of degree 1. So you run down this list looking for stuff in your integrand. As soon as you find something like here, oh, I do have a polynomial, you pick that piece to be u, and everything else is automatically dv. Remember, u times dv has to be your whole integral. You have to start with the integral of u times dv. This is called partitioning. When you take a set and you split it into multiple pieces, which together form the whole set, it's called a partition. We partition the integrand according to the Lipet rule, where you run down this list, and the first time you see something that's on this list, you make that thing u, and you make everything else dv. From there, it's very mechanical. You just fill out your table with your choice of u and dv. You calculate du from u, you calculate v from dv, and then you plug into this formula. And again, the hope is that the integral you get out is easier than the integral you started with. If it's not, you want to go back and try something else.
When you say exponential, do we substitute the entire thing or the exponent? Like, for example, e to the x.
The entire thing. So remember, we're not substituting here. We're partitioning. So we don't need to think about any inner and outer functions or anything like that. It's its own new thing. But yeah, you can pick the whole thing. So if I had like e to the 5x shows up in my integral somewhere, then and that's the first thing I run into on this list, then I would pick e to the 5x to be my u and everything else to be dv. Okay. For how much integration we've been doing, there are some very fundamental functions whose antiderivatives to us are still unknown. For example, how do you integrate the natural log? Let's do this one as a definite. No, we'll keep this one indefinite. No. No, this is not something we've seen. We know the derivative of ln x is 1 over x. We know that the integral of 1 over x is ln x, but we don't know what the integral of ln x is. Think about it, all the way through this class and back in Calc 1, this is not something you've ever bumped into. And this doesn't really look like a product, right? This isn't like something I would differentiate with the product rule if I was taking a derivative, but still integration by parts is the way to do it. I think about my Lipet rule. So I know I need to choose u and I need to choose dv. Really, I just choose u and then everything else is dv. If I think about my Lipet rule, do I have any logarithms in this expression? Yes, I do. So right away, I'm going to pick u to be that logarithm expression and everything else to be dv. So u is the ln of x and dv is just dx. Then from those, we calculate du and we calculate v. So du is the differential to get by differentiating ln x. The derivative of ln x is 1 over x. So du is 1 over x dx. And v is the integral of dx. Right? Integrate on both sides here. The integral of dv is v. The integral of dx is x. There's my little IDP table. And now we follow the recipe. The recipe says that the integral of u times dv is equal to the integral of u times v. It's the ln of x times x minus the integral of v times du. And you see a little bit the reasoning behind the LIPET rule. If you differentiate a logarithm, you get a nice algebraic function, no longer transcendental. The log goes away. When you differentiate it, you don't get more log stuff, you get just 1 over x. Okay, that's nice. It's even better that when you integrate dx, you get x. So in here, here's my here's my v, and here's my du. The x times 1 over x, those are going to cancel. And I'll just get 1 here. What do we have? I like to write the x in front of the ln x. So I write this as x ln x minus, and we just have the integral of 1 dx. And the integral of 1 dx, so just x itself, is x. So this is x ln x minus x plus c. There's a nice copy there for a little bit. And you can check, same sort of stuff we did on the previous example. You differentiate this, you'll need the product rule here. You will get ln x out. So this is your integral of ln x. It's x ln x minus x. Questions here? So he said integration by parts is a backwards product rule. That's 100% true. But you see here, you can also use it on a lot of things that don't look product rule, that don't look like you would differentiate them with the product rule. And the kind of deeper truth is that integration by parts is a really powerful method for attacking all sorts of problems. There's some really, really great shit in your textbook. If you look in your book, section 7.1, the problems towards the end of that section are phenomenal. And the truth is, integration by parts, we use it to prove things in differential equations, physics, all over the place. It's a powerful technique. I will use it to show you some pretty wild shit a little bit down the road, but first we just need to get a bit more practice with the basic things. We've done 2 indefinite integrals, so let's do a definite integral. Let's evaluate the integral from, say, 0 to 1 of, here's another basic function that we don't know how to integrate yet. Arctangent, or the inverse tangent function. I'm going to begin with a little note. Remember that the inverse tangent of x has nothing to do with 1 over tangent of x, which is cotangent. The inverse tangent function, this is sometimes called arctan x, it's the function yeah, we can think of it like this, that undoes the tangent function. All right, so the tangent function takes in angles and spits out numbers. The inverse tangent function takes in numbers and spits out angles. It has nothing to do with the reciprocal of the tangent function. Please don't forget this. It's its own thing. Like the previous problem, this doesn't look like a product rule sort of thing. But it is amenable to integration by parts because it's an inverse function. And we know our LIPET rule, the inverse is the second thing there. So here's what I'm going to do. Again, following my little rule here, I ask, are there any logarithms? Nope, not this time. Are there any inverse functions? Yes, sir, there are. So I'm going to pick that thing to be u. And that means automatically everything else is dv. And then I fill out my little table. U is the inverse tangent of x. dv is just dx. Now from u, I calculate du. What is the derivative of the inverse tangent function? What's the derivative of this guy?
One over 1 plus x squared.
Very good. So the differential would be 1 over 1 plus x squared times dx. And here v, the integral of dx, is just x. Now may be a good time to remind you, so shit like this, important. Shit like this, important. I have a place for you to remember all that important shit baked into Canvas. If you go to the modules, under the review material section, you will find, among other things, some trig. Specifically, you want to pay attention to the inverse trig. Got to make sure you remember what these things are and also how to take their derivatives. If you look elsewhere in here, you will find derivatives of inverse trig functions. So I won't take the time to go through that right now, but you got to make sure you remember just the basics, right? And the calc one. So we use LIPET to pick u and dv. We calculate the integration by parts table. And now I use my integration by parts formula. It says the integral from a to b of u times dv is equal to u times v evaluated from a to b. So this is the inverse tangent of x times x evaluated from 0 to 1 minus the integral from 0 to 1 of v times du, which is x times 1 over 1 plus x squared dx. Okay, I'll tell you right now, one of the places that I end up taking off points on exam 1 often, right here. Do not forget to evaluate the u times v piece between the bounds. If you're doing a definite integral and you're using integration by parts, remember you've got your u times v evaluated from a to b minus v times du from a to b. So with a definite integral, you need the evaluation here. This needs to be a definite integral. People often leave off either the bounds here or the bounds here, and doing either of those things makes it wrong. Right? This is a definite integral. Okay. Is this integral easier than the one we started with? Do we know how to integrate x times 1 over 1 plus x squared? Anyone got any ideas there?
Small u sub.
Small u sub, perfect. Another tip, it's nice to go ahead and do the evaluation here, right? Rather than like rewriting this highlighted part at every single step that follows, just go ahead and crunch this shit out. This is the inverse tangent of 1 times 1 minus the inverse tangent of 0 times 0. So 0 times anything is 0. And it happens to be the case that the inverse tangent of 0 is 0 anyway. So that part is definitely 0. I'll go ahead and rewrite the rest of the problem here, which is integral 0 to 1. All right, this says x over 1 plus x squared dx, just to conserve space. Multiplying something by 1 just leaves it alone. What is the inverse tangent of 1? Or arctan of 1, what is that?
So 1.
It's not, sorry, it's not that nice, right? This is the unique angle from negative pi over 2 to positive pi over 2, such that the tangent of that angle is 1. In fact, let me go ahead and just remind you the exact definition. We say the inverse tangent of x is equal to theta if and only if a pair of things are true. The tangent of theta is equal to x and negative pi over 2 is less than theta is less than positive pi over 2. So the inverse tangent of 1, this is going to be an angle in radians between negative pi over 2 and positive pi over 2, such that the tangent of that angle is equal to 1. Where is the tangent equal to 1?
Pi over 4.
Very good. So this is pi over 4 times 1 minus 0 times 0. Okay, that's just pi over 4 minus this integral. It was suggested how we do this integral. We should do a little u sub. Now, because I'm using the letter u elsewhere, we do not want to use the letter u again. Z is nice. What should I substitute for in this integral over here?
1 plus x squared.
Good, sub for the bottom. Why? Because the derivative of 1 plus x squared is 2x. So my differential is 2x dx. In other words, this x dx is going to be 1/2 dz. Now, what else happens when I make that substitution? The bounds change. When x is equal to 0, z is equal to 1 plus 0 squared. So 0 goes to 1. And also, when x is equal to 1, z is equal to 1 plus 1 squared. So 1 gets mapped to 2. All right, there's all the stuff from my substitution. So this first piece here, all this stuff is just pi over 4. Minus is this minus. And then we have integral 1 to 2. X dx is 1/2 dz. And downstairs here, I have a z. So this is integral 1 to 2 of 1 over z times 1/2 dz. That's how that substitution shakes out. We can pop the 1/2 out of the integral, and then we're just left with integral from 1 to 2 of 1 over z dz. And that's done just using the regular fundamental theorem of calculus. I know the integral of 1 over z. What is that?
Ln x.
Ln of z. Yeah.
Ln z.
So this would be pi over 4 minus 1/2 times the natural log. If I'm being careful, I put absolute values there. Evaluated from 1 to 2. And remember, when you do a u sub in a definite integral, you change the bounds. You don't need to go back to the original variable. You just evaluate this between these bounds. That's the point of changing the bounds, or one of the points. And remember, I require you to do that. You must change the bounds when you do your substitutions. So as you practice these problems, do them like this. Last step here is to evaluate that last bit between bounds. So you have pi over 4 minus 1/2 times the ln of the absolute value of 2. The absolute value of 2 is just 2, minus the ln of the absolute value of 1. And again, absolute value there doesn't do anything, doesn't change anything. Does anybody know what this is off the top of their head?
Zero.
0. Very good. Natural log of 1 is 0. Does anybody know what this is off the top of their head?
Nope.
Yeah, I'm just fucking with you. This one, it's just nasty. There's no nice way to write that. So we just get pi over 4 minus 1/2 times the natural log of 2. That's it. That's the game. Questions on this one?
On the test, will we be required to put absolute values or?
If you in this step omitted the absolute values, I wouldn't take off points. However, it's worth noting that I could do this integral from -2 to -1, right? I could make both those bounds negative, and then you would be in trouble here without the absolute values. So make sure if you need them that they are there. If your integration is running over anywhere that you could have a negative output, I'm sorry, negative input for your bounds, then make sure you use the absolute values. Good question. Other questions on this?
Wouldn't you put 1 plus x squared back in?
If I was doing an indefinite integral, an integral without bounds, then at this step, rather than plugging in my new bounds, I would plug in the old variable stuff. But we're doing a definite integral. And remember, when we do any sort of substitution in a definite integral, we always change our bounds. And then you don't need to go back to the original variable. You just evaluate your new stuff between the new bounds. Remember, these are the old x values. These are the new z values. The new z values are all you need to plug in at the end. We talked about this a little bit in the first week, and I will remind you, it's under here. Why do we always change bounds when substituting in definite integrals? You can check this out. The idea is after making your substitution, you've changed the coordinate system. So if I wanted to find all the area, say, under this blue function from 1 to 1.5, that's the same as all the area under this red function from 0 to 0.5, right? You see the regions have the same shape, same area. So when you do a definite integral by substitution, you should always change your bounds. You should always change your bounds, and then you don't have to go back to the original variable. Moreover, if you didn't change your bounds, if you wrote this as 0 to 1, that's just straight up incorrect. 1 over z isn't even defined when z is equal to 0. So you always got to change those bounds. And then having done that, you do not need to go back to the original variable. All right, what else are we thinking? If this was the test, it's just this question, what are we worried about? Everything else feels good? Okay. Then for my next trick, for our next little example here, show you one of the ways integration by parts can get a little bit tougher. There are many ways, but sort of one of the classics. Something like this maybe. So I have a polynomial multiplying some transcendental function like e to the x, sine x, cos x, anything like that. In this case, that polynomial is of degree 2. You know that when I differentiate e to the x, or integrate e to the x for that matter, it always stays e to the x. So in order to make this thing nicer, what I'd like to do is differentiate this guy. See, if I differentiate this guy once, he's going to go from being quadratic to being linear. And if I differentiate him twice, he's going to become a constant. So the trick to evaluating integrals like these, polynomial times exponential, is to run integration by parts multiple times until the polynomial piece is no longer causing you trouble. So this is one example, but it's characteristic of a whole family of problems. Anytime you have a polynomial times e to the x, sine x, or cos x, you will do the same thing. You'll follow your LIPET rule to choose u. Are there any logarithms? No. Are there any inverse functions? No. Are there any polynomials? Yes, there are. This piece is a polynomial. So he's going to be u. And that means everything else has to be dv. So u is x squared plus 3x. And dv is just e to the x dx. Don't forget to write the differentials. Du, the derivative or differential of x squared plus 3x is 2x plus 3. And that whole thing is multiplied by dx. The parentheses here are important. V, if I integrate e to the x dx, I just get e to the x again. So here's our little integration by parts table. And then applying my IBP formula, I see that this integral is equal to u times v. So that's x squared plus 3x times e to the x minus the integral of v times du, which is e to the x times 2x plus 3 dx. Now remember what I said at the start of class. All right, IBP always takes your original integral, spits out some shit, and another integral. You should ask yourself, is this integral better, nicer than the original integral? And the answer here is yes. Yes, it is. So what's causing this to be problematic is the polynomial, right? If that wasn't there, if you just had to integrate e to the x, that's easy. And by running this integration by parts once, I've taken the polynomial from a degree 2 polynomial quadratic down to a degree 1 polynomial linear polynomial. So yeah, this integral is better than the original. It's nicer, it's closer to being solved. How do you think I should proceed from here?
Another IBP for 2x plus 3.
Yeah, very good. So the same ethos applies. This is a polynomial times an exponential. So I'll pick this piece to be u and everything else to be dv. So I'm going to run IBP again. U is going to be 2x plus 3, and dv is going to be e to the x dx. This stuff is my dv stuff. Then, just like in the first step, we complete the IBP table. We do that by differentiating u to get du. It's going to be 2 dx. And you integrate dv to get v. That's going to be e to the x. So what do I get? Well, this piece is still here. This piece hasn't gone anywhere, so don't forget to write him down. X squared plus 3x times e to the x minus, and then I will open up a big parentheses or a big bracket because this minus right here is going to need to be distributed over all the stuff that comes from this integration by parts. You're about to replace this integral by a difference of two terms, right? uv minus the integral v du. That means that this negative is going to need to be distributed over those two terms. What are those two terms? Well, 2x plus 3 times e to the x, that's u times v, minus the integral of v times du, which is e to the x times 2 dx. You see what I mean? There's multiple terms here. And since we were subtracting this integral, we need to be subtracting this whole thing. Now we'll distribute the negative, evaluate the integral, and call it a day. So I get x squared plus 3x times e to the x minus 2x plus 3 times e to the x. And then minus here makes plus. I'll pop out the 2 integral of e to the x dx is what's left. Everybody with me up to this last line? Now things are easy. I know the integral of e to the x. That's just e to the x. So we're going to get x squared plus 3x times e to the x minus 2x plus 3 times e to the x plus 2 times e to the x plus. And looking at this answer, you may notice a pattern. My original choice of u was x squared plus 3x, and my original choice of dv was e to the x dx. This is like the polynomial times the exponential minus the derivative of the polynomial times the exponential plus the second derivative of the polynomial times the exponential. It's an alternating sum of derivatives and antiderivatives. And there is a nice way to kind of condense those two IVP tables into a single IVP table. Very creatively named tabular integration by parts. So integrals of this form like polynomial times exponential or sine or cosines dx or whatever. These are always done this way. By running IBP multiple times. Which is determined by the degree of the polynomial. The procedure can be condensed using what's called tabular integration by parts, which is not an official part of the Calc 2 curriculum here at Santa Fe, but it is at UF and some other schools. So I invite you to Google tabular integration by parts, because it will allow you to do things like this a little bit quicker. Basically, you just have one column that is repeated derivatives and the other column is repeated antiderivatives, and you form a kind of alternating sum. You differentiate the polynomial till it's 0, and then you form this alternating sum of derivatives times antiderivatives. It's not necessary, and on a test, I'm not going to give you like a degree 5 polynomial times e to the x and ask you to run IBP 5 times. But integrals of this form do show up surprisingly often out there in the real world. So it is nice to know how to do them, not just point blank, but nice to know how to do them quickly when possible. So yeah, tabular IBP is a thing. It's not necessary. You can always do exactly what we did here. And on a test, this is what I would expect from you. But if you want to self-teach tabular IBP, you're welcome to do that. Any questions on how we were able to evaluate this integral? Why we got this answer? Okay. Let me see how we're doing for time. All right, 10:29. About 15 minutes, right? Where do we go? There it is. All right. In those last few minutes, let's see, I could start showing you the damped harmonic oscillator, or we could look at another example. Let me grab another example. Let me take a look at your textbook. Rather than, so there's a whole other family of integrals called looping integrals, looping IBP, which are important, a little bit tricky, but I'm trying to decide if we want to go that far right now or not. Yeah, that's the next one they do. I don't know. Arctan did that. maybe it would be fun to look at something a little less wild. Okay, so first, these are sort of the problems that I was talking about. These, when I said there are some really great problems in this section, the latter ones, pretty much anything after 47 is really, really good stuff. Let me go ahead and show you something. Some integrals can be solved by using IDP to turn the calculus problem into an algebra problem. And these are called looping integrals. The classic example something like e to the negative x times cos x. The graph of this function is interesting. So cos x, you know, it's a wave. E to the negative x, you know, is a rapidly decaying exponential. And when you multiply the two of them, you get the wave from the cosine, but it is shrunk down by the rapidly decaying exponential. I'll adjust my axes a little bit. The x's, we're going to just go from 0 to, say, 10. Oh, no, let's do 0 to 50. And then my y values, these can be quite small. So 1 and 5. Something like this. What's going on here? It's still hard to see at that scale because this decays so fast. What's going on here is something like, let me draw it for you. You remember the graph of sine x over x from your Calc 1 class? It's a lot like that. You have a rapidly decaying exponential that is bounding your oscillations in the cosine function. So the dashed thing here is like e to the negative x, and this thing, of course, is like cos x. But the cos x wave is being squished down hard by the e to the negative x. This is called the damped harmonic oscillation. So regular old sines and cosines are called harmonic oscillators because they bounce back and forth, they oscillate. And the e to the negative x term here is like a dampening term. It squishes the harmonic oscillator. These show up in the physical world all the time. A swinging pendulum will slowly swing less and less, but it'll keep going back and forth. Shit like that. So knowing how to integrate exponentials times trig functions, specifically sines and cosines, pretty important in the world of physics. This is also done by parts. If you follow your Lipet rule, do I have any logs? No. Inverse functions? No. Polynomials? No. Exponentials? Yes. And dv? Cosines. Du then would be negative e to the negative x dx, and v, the antiderivative of cos x, is sine x. So that integral e to the negative x plus x dx is equal to u times v. It's e to the negative x times sine of x minus the integral of v times du, which is sine x times negative e to the negative x dx. So with one run of integration by parts, I get some shit spit out and then another integral that looks similar to my original integral, right? Similar to the original. It's just that the cosine has been swapped for a sine. If you pull this negative out and write the exponential term first, you get your e to the negative x sine of x plus integral e to the negative x sine of x dx. So one run of IBP turned the cosine into a sine and didn't do anything else. What do you think a second run of IBP might do?
Switch it back to a cosine and we're gonna have a looping.
Yeah. So if I run IBP on this, that will spit out another term that looks kind of like this, and an integral of e to the negative x times cos x, which is my original integral. And that's what I meant when I said it turns the calculus problem into an algebra problem. You will have your original integral equals some shit minus your original integral. That's actually an equation you can solve for the integral. Let's do it. So if this melts your brain a little bit, don't feel bad. In your second run of IBP, you need to pick u and dv the same way. Follow the Lipet rule again. Exponential, that's your u. So dv is sine x dx. Therefore du is negative e to the negative x dx. And v, this time you're integrating sine, that's negative cosine. So here's my second IBP table. We get e to the negative x sine of x, still chilling here from the first part, plus this integral is equal to e to the negative x times negative cos x. I'm going to write that as, well, I'll write it like this. E to the negative x times negative cos x minus the integral of v times du, which is negative cos x times negative e to the negative x. Be very careful with your minus signs, right? The one theme with integration by parts problems is because the formula has a negative in it, and when you differentiate and integrate many common functions, you get negatives out. You can have lots of minus signs piling up. Like here I have 1, 2, 3 minus signs piling up in this guy. You need to be quite careful. So negative cos x times negative e to the negative x is cos x times e to the negative x, right? So overall, that last term there is going to be negative. This is e to the negative x times the sine of x. This piece, e to the negative x times negative cos x, I would write that as minus e to the negative x times cos x. And then this piece minus negative cos x times negative e to the negative x is minus integral. All right, that e to the negative x out front, e to the negative x cos x dx. So here's the magic. Your original integral is equal to this stuff minus your original integral. Let me just rewrite the left-hand side. Integral e to the negative x cos x dx. Now you stare at this until you realize something magical has happened. This thing, which is the thing we're trying to find, is equal to this stuff minus the thing we're trying to find. if you add this integral to both sides, then you have this integral plus itself, which is 2 times that integral. And that's equal to e to the negative x sine x minus e to the negative x cos x. At this stage, we'd normally write the plus c, but I'll issue it for now just to help you see the algebra. I'm just adding this piece to both sides. So over here, it goes away. Over here, I have this thing plus itself, which is 2 of that thing. And on the right-hand side, these pieces just come along for the ride. Now divide both sides by 2. And at some point, we got to write the plus. That's it. That's it. So it kind of feels weird. It kind of feels magical in the sense that like I'm never really cooking this integral up. I do 2 runs of IBP, and then I get this equation. You know, my integral is equal to some shit minus my integral. It's kind of, like I said, kind of feels magical. It kind of feels weird, but it works. These are called looping integrals. Looping integration by parts. Damped harmonic oscillators are one of the kind of families of integrals where you do this. So anytime you have like e to the ax times sine or cosine of bx, this is going to be the path. It's not the only one. Odd powers of secant and cosecant both are integrated like this as well. And I'll show you those next time. All right, what's today? Wednesday? I'll show you those on Friday. So next time we're going to see more looping integration by parts. We'll get a little bit more practice just solving IBP problems. You do have a new homework that's coming up today. So please watch out for that. It's not up right now, but it will be up soon, and it's going to be due on Monday of next week to kind of get us on schedule. That's it from me for today. So welcome to the hard part of the class, or the kind of middle hard part of the class, where we're actually starting to learn some new integration techniques. Remember to stay on top of your shit and it'll be all right. Okay, just don't fall behind. Work hard every day. You'll be good. If you need to talk to me, office hours this afternoon, 1 to 2 p.m. You can send me a Canvas message or hit me up on Discord. Take care, guys.
Thank you.